So sigma notation is going to allow us to write big sums in a nice compact manner. So here's what the sigma notation looks like. Yes, it is this sigma, this capital sigma, Greek symbol, Greek letter, and really for sum. All right, so here's what it says here. We're going to take the sum from I equals 1 to I equals n of all terms described by AI. So we're doing a bunch of a's and incrementing them by 1, starting with I equals 1. Hence we have a1, then next one up is a2, a3, and we're going to add all of those a's until we get to an. So that's what that notation is saying. Again, it's summing from I equals 1 to n, a sub I. All right? This I is the index of the summation. AI is the ith term of the summation. 1 and n are the lower and upper bounds of the summations respectively, starting at 1 lower and going to n. And AI is our general ith term. So all these terms are going to look very similar. They're just going to be different potentially based on what I is, what number term this is. For example, what if we want to do sum I equals 1 to 4 of I? All right, well, there's going to be 4 terms. So when I equals 1, the term I just looks, the term AI just looks like I, so it's just 1. And then when I is 2, we just get 2. When I is 3, we get 3. And then we get 4. Adding these up, it's 3, 6, 10. So what we've seen is this representation actually asked us just to add up the numbers 1, 2, 3, 4, the first 4 counting numbers, and get 10. So that was a way of doing that. It's a nice compact way. What about the sum j equals 2 to 5 of j squared? Well, we start this time with j equals 2. When j equals 2, j squared is obviously 2 squared, then 3 squared, then 4 squared, then 5 squared, and I stop because now I'm at j equals 5. So if I add these up, that's 4 plus 9 plus 16 plus 25, I get 54. So what I did was I squared the numbers from 2 to 5, the counting numbers from 2 to 5, the whole numbers. So what about this one? Sum k equals 1 to 3 of 5. Interestingly enough, every term just looks like 5. So when k equals 1, I get 5. When k equals 2, I get 5. When k equals 3, I get 5. And so I get 15. So what we see is that this is a nice way of writing it, but we're going to need some more tools in order to do big versions of these. Like instead of summing from I equals 1 to 4, maybe we want to do I equals 1 to 20,000. And if we had to keep going and doing what we're doing here and writing them all out, then we would have defeated the whole purpose. So we've been able to come up with some summation formulas that give us an idea of being able to do this without writing it all out. So as we saw in the last one, if you sum the same constant c, I equals 1 to n, you're really just adding c n times. That's the same thing as getting c times n, which is in fact what we got back here. We added 5 3 times. So we got 5 times 3, or 15. So that one makes a lot of sense. All right. The next one, summing up I from 1 to n, is a big historical problem. And basically, this goes back to a story which, although has been shown very likely not to have been true, or not true at all, but attributed to Gauss as a little boy in school, so the mathematician Gauss. And it was said that on one day when his teacher was really tired and didn't want to do some work, the teacher asked the students to add up the numbers from 1 to 100, thinking that they would have to spend a lot of time doing that and the teacher could get some rest. Well, as the story goes, Gauss thought about it for a couple of seconds, raised his hand, and gave a correct answer. And the idea was, how could he do it so quickly? Well, this is how. If you want to add up the numbers from 1 to 100, like this, that looks like a daunting task. But actually, if you think about doing it twice, so this time I'm going to add it 1 to 100, I'm going to do it backwards. 100 plus 1 plus 99 plus 98 plus, and then all the way down to 3 plus 2 plus 1. All right, we see that both of those are ways of adding from 1 to 100. But if I do them together, and notice that each term here, if I added them, is 101. So I'm actually just adding 101 100 times. So I would just be doing 101, or sorry, I would do 100 versions of 101. But the fact is, I counted them up twice, so I divide by 2 to get my answer, which is 5,050. So that's the sum of adding up the numbers from 1 to 100. That generalizes in basically saying if you want to go from the sum of 1 to n of I, so just count the numbers from 1 to n, add them up, it's n times n plus 1 over 2, just like we found over here. So that's very useful. So we don't have to use a formula over there. If we went back to this one, when we did 1 to 4, that would be n of 4 times n plus 1 is 5 over 2, and we see we do get the 10 that we found there. So there are ways to then manipulate that into getting the sum of I squared and then the sum of I cubed as well with these end results. One last thing about this is, are there some summation properties that make dealing with these easier? Yes. If I always have the same constant in every term, then I should be able to pull it out. Right? That's a basic factoring idea. If you have n terms being added together and they all have the same factor, you can pull that factor out and then multiply that by the remaining sum. And we can do that with these big summations as well. The other thing is, if you have two different sets of numbers that you're adding at the same time, so you have AIs, and you're either adding or subtracting BIs, and then you take the sum of what you get out of that, you could do that separately. You could break that and do all the sums of all the A's and the sums of the B's and either add or subtract them as you were intending to do.